Hi guys, and welcome to today's video. In today's video, we're gonna see how critical and important the role of the nested vector interrupt controller within an ARM Cortex-M microprocessor, and how we're gonna use it to properly handle and manage the different interrupts supported by our platform. We'll see how we can enable and disable separately each interrupt line, and how we can track the interrupt line state using our NVIC registers. And we'll finalize our today's video by a demo running on STM32 based platform. From functional point of view, the NVIC controller is playing the role of the hardware block sitting between our CPU core and the different peripherals interrupt lines. Hence, the NVIC controller allows the forwarding of the different interrupt lines events to our CPU core. Because of that, the NVIC controller allows the enabling and disabling of the different interrupt lines separately. It allows as well the tracking of the state of the different interrupt lines, whether they are in active state, means the CPU core has already received the interrupt line event and has jumped to the corresponding ISR handler, or in pending state, it means the CPU core has already received the interrupt line event but didn't jump yet to the corresponding ISR handler, or not active state. NVIC allows as well defining the priority of each interrupt line separately. Based on those functionalities, we can see how important and critical the role of the NVIC to handle and manage the different peripherals interrupt lines. From lifecycle perspective, any interrupt can be in one of those four supported states. Those states depends if the NVIC has already forwarded or not the corresponding interrupt line trigger. Also, if the CPU has already served or not yet basically the received interrupt line trigger, and we jump it basically to the corresponding ISR handler. The interrupt can be in inactive state, means there has been no trigger coming even out of the peripheral. In pending state, means there has been an interrupt line trigger coming out of the peripheral and has been either gated by our NVIC or already forwarded by the CPU, but the CPU has not yet jumped into the ISR handler. Or active, it means the interrupt line event has been forwarded to our CPU via the NVIC controller. The CPU has already received this interrupt line event and had jumped to the corresponding ISR handler and started executing the different instructions within the ISR handler. And finally, the interrupt can be inactive and pending. It means the CPU has already jumped to the corresponding ISR handler, but then it received back-to-back interrupt line event coming from the same peripheral. In terms of programming model, the NVIC controller has a set of registers that allow enabling and disabling each interrupt line separately, as well as tracking the state of each interrupt line separately. We have those ESCR registers that allow enabling or disabling the forwarding of each interrupt line separately to our CPU core. Each bit actually of those registers is connected to a single interrupt line. If it is set 1, then the interrupt line event will be forwarded to our CPU core. If it is cleared, then this interrupt line event will not be forwarded to our CPU core. Then we have a set of registers that allow clearing basically the enable of those interrupt line forwarding events. Hence, if we set that bit to 1, then we can here in this interrupt clear enable register, then we are clearing basically the corresponding bit within this ISCR register. Then we have the pending register. Now, if our interrupt line event has been actually received by the NVIC controller, then the state of this interrupt will move to pending state. And the corresponding bit to that interrupt line within this ISPR register will be set to 1. This indicates basically that our interrupt has been triggered, but not yet served by our CPU core. Those registers are writable, means we can fake basically the triggering of the interrupt line event from CPU perspective. So there is no need to receive explicit interrupt line event from the peripheral. We can just go to this register and set the corresponding bit for that interrupt line to 1, and hence we can move the state of that interrupt line to pending. And from that perspective, we can even trigger the jump to the ISR handler from CPU perspective without even receiving a real interrupt line event. So this is a powerful feature within our NVIC controller. We can clear the corresponding pending bit via this interrupt clear pending registers, as you can see. So each bit of those clear pending registers is matching basically a single bit of this interrupt set pending register. So it's the same feature as enabling as well, as you can see. Then we have the interrupt active bit registers. This indicate if our interrupt line is in active state or not. Active state means the interrupt line event has been forwarded to the CPU core, and the CPU core has served already the interrupt line event and jumped to the corresponding ISR handler. So this allows tracking the active state of our interrupt, and even we can, via software, trigger the changing the state of the interrupt to active. Means we can go to the corresponding bit within this active register and set that bit to 1. Then we can enforce the interrupt to move to the active state, and the CPU then will jump to the corresponding ISR handler. Again, this is very powerful feature within our NVIC controller. Then we have, of course, this interrupt priority register. Now each byte, so not bit, each byte means each 8 bits within those registers is matching basically a single interrupt line. And hence we can have up to 255 priorities for our interrupt lines. Finally, we have the software trigger interrupt register. This allows triggering via software the interrupt line event. So similar kind of to pending. So we don't need to receive a real interrupt line event coming out of our peripheral. Just we go to this register and then we program the corresponding interrupt line number within this register, and this will trigger explicitly basically the moving of the interrupt line to pending state, then to active state once the CPU had jumped to the corresponding ISR handler. As we will need in any embedded software-based application using an ARM Cortex-M microprocessor of frequent access to our NVIC registers to set up our interrupts, ARM has already provided a set of macros that abstract the access of the different NVIC registers from user perspective, and those macros are part of what is called CMSIS headers. Hence, instead of developing our own driver or APIs to access those NVIC registers, we can use just those CMSIS-based macros or APIs provided by ARM to set up our NVIC for specific interrupt lines. And this is very useful for our embedded software application, as you can see. So guys, this is our KEIL-MDK based project. As you can see, this is a C-based project that has been compiled for an ARM Cortex-M based platform. Our platform is an STM32 microcontroller, and the project has been already compiled, and the binary has been already loaded into our target device. And we started already a KEIL-MDK debug session. Now in terms of code, we are enabling basically the interrupt line number 0, which is matching this watchdog window timer interrupt line. This is supported by our STM32 microcontroller. We are using here basically the CMSIS based macro that allow enabling the IRQ line from NVIC controller side. And then we'll try via software, not peripheral, but via software basically to fake the interrupt line event triggering, so that we trigger a jump to our watchdog window timer interrupt handler. Right now we are having a default implementation for the different interrupt lines. So if we go back to our startup code and to be more precise to our vector table, we can see that all interrupt lines basically are mapped to this default IRQ handler. And hence, we are overwriting basically the implementation of this default IRQ handler here. And whenever we are triggering basically the interrupt line number 0 event, we should jump basically to this handler, as you can see here. Here I am writing to this software triggering interrupt register. This is a software way basically to fake the triggering of each interrupt line separately, and we need to write the interrupt line number to this register. This is the line number 0, so the ID should be 0. If it is interrupt line number 1, then the ID should be 1, and so on. Now this has been loaded, so let's enable our interrupt line number 0 via the NVIC. Then we jump here, and then let's set breakpoint here, and then run, and here we go. As you can see, we have jumped basically to our default IRQ handler. So our interrupt has moved from inactive to pending state, then from pending to active, and then we are executing basically the instruction within the corresponding interrupt or ISR handler. Our interrupt line is number 0, so we need to add, let's say, this interrupt line on top of the, let's say, existing internal exceptions. We will have already 15 exceptions, and this will be number 16. So the numbering of this interrupt line number 0 will be 16. So we need to always count from the beginning of our vector table, not from the beginning of those different external interrupt lines. And as you can see in the XPSR register, and to be more precise in this ISR one, we can see that the active interrupt line right now is number 16, which is matching basically our interrupt line number 0, which is of course the window watchdog timer. Now let's try to trigger basically or fake the trigger of the interrupt line number 0 using the pending register. So we'll comment out this part, and then we uncomment basically the line where we are setting the corresponding bit of our pending register. Then of course we'll try to compile our project. Done. And then we're gonna try to load the binary again into the STM32 flash memory. So far so good. Now we'll set a breakpoint here. And what will happen, we are going to set the corresponding bit of the pending register that is matching this interrupt line number 0, or our window watchdog timer. And once we do so, the interrupt line will move to the pending state, and then based on the priorities and so on, the CPU may or may not serve basically this interrupt line and jump to the corresponding handler. For now, we don't have any, let's say, concurrent interrupt lines in active state or higher priority basically interrupts, and hence once we move the pending bit to 1, then the CPU actually will serve this interrupt line event and then move it to active state and jump to the corresponding interrupt line handler, as you can see here. And even we can match basically the ISR field with our interrupt line numbers. So this is 16. We again count from the beginning of our vector table, not from the beginning of our external interrupt lines. So this exactly match our window watchdog timer interrupt line.